Hi guys, so I'm going to be explaining chapter 1 for the chemistry periodic. Okay, so the first question, it says after the gaseous system has reached equilibrium, so we're obviously at equilibrium, and the total pressure has been reduced. And they're saying what is expected to happen when you reduce the pressure. So whenever it's pressure and volume, you're gonna count the moles and then move to the side with more moles if you're trying to reduce the pressure. If you're trying to increase the pressure, you're going to move to the side with less moles. So since they said they're going to reduce the pressure, we're going to move to the side with more moles. So let's count the moles. So here, 1 and 3. You're going to add them, you're going to get 4 moles on the side. And then here, it's 2 moles. So which side has more moles? Obviously the 4. And since they reduced the pressure, we have to go to the side with more moles. So we're going to move backwards like this. Okay, so now we're going to answer. The backward reaction is favored, yeah, because we're going backwards. The position of the equilibrium is not shifted as there are gases on both sides. That's not true. It's only if there's equal moles. Let's say on the reactants there's 4 moles and on the products there's also 4 moles. That's when it doesn't move, okay? But when it's gases on both sides, it doesn't really matter. The pressure of NH3 is reduced, yeah, because NH3 is in the product, and since we're going backwards, it's gonna go less. So that's correct. And the system favors the formation of H2 gas. H2 is here. N2 and H2, the system would favor getting more H2 and more N2 because you're moving backwards. That's it. This is easy. This is the answer because it's going up, down, up, and it's stable. It makes it stable. That's why it's at equilibrium. Okay, so the question is saying which of the following are true about a system at equilibrium. Equilibrium means that the backward and forward reaction are happening at the same speed, so they're going backward and forward at the same rate. Okay, so the first one says the macroscopic properties are constant. Macroscopic means something you can see with your eye, okay? For example, let's say the color is constant, or the concentration is constant, or the temperature, or the what you can see. So let's say color, you added something and the color is constant. That means that the solution isn't at constant, is at equilibrium. So that's why this is correct, because constant means equilibrium and you can't see any change happening after that. The forward and backward reactions take place at the same time at equal rates. This is the meaning of equilibrium. You need to know this. The microscopic processes continue to occur. Microscopic is something you need help to see, not with the eye, macroscopic. So continue to occur, yeah, it will never stop. It will keep going backward and forward at the same rate. Yeah, that's correct. And both the reactants and products are present at equilibrium. You need the reactants and products to both be present and happening at the same rate. I can't explain it, that's just how it is. And yeah, basically this question is kind of memorizing. I'm just trying to explain it in a way where you don't need to memorize. And the forward reaction is favored. The forward reaction or the backward reaction can't be favored. They both have to be equal for it to be at equilibrium. This is why this is wrong. Okay, another question about equilibrium. It says which of the following statements is true about the state of equilibrium. Okay, so the first one says both the reverse reaction and the forward reaction stop when the system reaches equilibrium. When the system reaches equilibrium, the forward and backward reaction don't stop. They just keep happening at the same rate. So this is wrong. The rate constants for both the forward and reverse reactions become equal at equilibrium. Normally, if you read this fast, you'd think, okay, this is correct, because they do become equal at equilibrium. But the rate becomes equal at equilibrium, not the rate constants. So if you ever see the rate constants for both the forward and reverse reactions are equal, it's wrong. The rate is correct. The rate is going to be equal, but rate constant is no. Usually rate constant is different at equilibrium. So if they said constants, it's wrong. A change in the amount of solid reactant in the reaction does not affect equilibrium. This is correct. Solid and liquid don't affect the equilibrium. Okay. The equilibrium tends to favor the state of the greatest potential energy. Remember, equilibrium doesn't favor anything over anything. They both have to be equal. So there's no favoring in equilibrium. Okay, the last one is kind of confusing, but I'm gonna try explain it in like a simple way. So they said when Q, let's think of Q as like where we are right now, okay, where the reaction is right now, and K is like the goal for like the perfect equilibrium, like the perfect amount of products. The reaction proceeds to the right, so we have to see if it does proceed to the right. So like I said, think of K as the goal for like the perfect amount of products, and Q is like where we are right now. So if our current Q is less than the goal, because it says Q is less than the goal for the perfect products, so how will we make the products more to get the perfect amount of products? So basically our Q is less than the goal. That means we haven't made enough products yet to reach the goal. How will we reach the goal to make higher products? We're gonna move to the right to like make more products. I'm trying to explain it in a simple way, but it's like kind of confusing. But yeah, so Q is where we are right now. K is our goal. Since Q is less than the amount of products we need to increase the amount of products, so we need to move to the right to make more products. So this is gonna be correct. Okay, here it says which of the following can alter the equilibrium of the above system. So we're gonna look at this, like what they gave us. They gave us solid, aqueous, aqueous. Okay, so now we're gonna read the options. Changing the temperature, how does it affect the equilibrium? Yes, it does. Like let's say you change the temperature and it was here. Okay, it will affect whether it goes backward or forward. So it does affect. Adding a catalyst doesn't affect equilibrium, it only speeds up the rate of reaction, it doesn't change it. Changing the concentration of a product, if you change the concentration of a product, obviously it's gonna alter the equilibrium, because if you add like more of Cl minus, it's gonna like want to move backward. If you added more PbCl2, it's gonna want to move forward. So it does affect the equilibrium. Changing the volume of a container, volume and pressure, remember they're like the same, they don't affect unless it's gas. And see here it says solid, aqueous, aqueous, there's no gas, so it doesn't affect equilibrium. Here, which of the following factors would increase the concentration of CH3OH? Okay, this is what they want to like increase. Okay, adding a catalyst will never like increase anything or affect anything. It only speeds up the rate of reaction to reach equilibrium faster, but it doesn't really affect anything, so this is wrong. Decreasing the temperature, if they decrease the temperature, the system will try to increase the temperature. So this is the temperature. Okay, if you're gonna increase it, you're obviously gonna move forward. So moving forward will increase the concentration of CH3OH. So this is correct. Decreasing the pressure. If you decrease the pressure, wait, we have to count the moles first. Sorry. So there's 3 moles on the side, and there's 1 mole on the side. Okay, so decreasing the pressure, remember how I said, I don't know which question it was, maybe first or something, I don't know. Decreasing the pressure will make the like thingy go to the area with more moles. So which area has more moles? The reactants has more moles, so it will go backwards, which will make CH3OH decrease. This is going to be wrong, because decreasing the pressure means going to the area with more moles, and CH3OH, which is the products area, doesn't have more moles. Okay, decreasing the volume. volume and pressure are the same, but they're like different in a way. So if you decrease the volume, the system will try to increase the pressure. So you know how we said decreasing the pressure, they'll go to the side with more moles. Increasing the pressure will go to the side with less moles, and the less moles is on this side, the product. So it will move forward, making CH3OH increase the concentration. This is why this is correct. So decreasing pressure, decreasing pressure will move to the more moles, and increasing pressure will move to the side with less. Yeah. Adding helium gas, this is not gonna do anything, because if you add an inert gas, it doesn't affect. How to know if it's like something's an inert gas? You go on group 18, which are the noble gases. So if you ever see these, that they added any of these, it's not gonna do anything because these are inert. That's it. Okay, for this question, it's saying which of the following factors would shift the equilibrium to the left. So we have to see the statements and pick which one would make the equilibrium shift to the left. So decreasing the concentration of SrSO4. Since this is solid, and we said solid and liquid cannot affect equilibrium, so this cannot work. So decreasing or increasing the concentration of SrSO4 will not affect equilibrium whatsoever. But let's say it was gas, okay? Let's say this is gas. Decreasing the concentration of SrSO4 would make the system try and increase. And how would you make it increase? By moving to the left. So this would be a correct statement if it was gas, but since it's solid, it doesn't affect. Increasing the concentration of SR2+. SR2+ is here. If you want to increase the concentration, the system will try to decrease the concentration. And how will they decrease the concentration? By moving to the left. So yes, it does move to the left. Decreasing the pressure. Okay. Usually we'd be like, okay, decreasing the pressure, it goes to the area with more moles. That's why it's not the answer. But it's not the answer for another reason. Because there's no gas. And remember, we said pressure and volume only works on gas. It doesn't work on it doesn't work on solid or liquid. So this is why this is wrong and this is wrong. But let's say it was gas. Okay? This would be wrong and this would be correct. But since there's no gas, again, these are both wrong. Increasing the number of moles of SO4. So if they increase the number of SO4, the system would try to decrease the number of SO4 by moving to the left. So this is why this is correct as well, because you're moving to the left. Which of the following would increase the yield? Okay, yield is products. So they're saying which of the following would increase the products. The only way to increase the products is by moving to the right. We need to see which of the following statements will make the products more. So move to the right. Increasing the pressure. Since there are gases, so we can use these actually. So increasing the pressure, and remember how we said if you decrease the pressure, you will move to the side with more moles. Increasing the pressure, you move to the side with the less moles. So here, how many moles do we have? We have 3. Here we have 2. Which area has less moles? 2. So it will move to the right because you're increasing the pressure. So this is correct. Decreasing the temperature. Since this is negative, it's going to be exothermic. So plus 4A2. So if they decrease the temperature, the system will try to increase the temperature. And by increasing the temperature, you have to move to the right to make the temperature more. That's why this is also correct. Decreasing the volume. Remember when we said decreasing the volume, the system will try to increase the pressure. So, and since we said increasing pressure is correct, that means decreasing the volume would also be correct. Adding a catalyst does not increase or decrease the yield, or it doesn't even affect equilibrium. Like we said, it speeds up the rate of reaction to reach equilibrium faster, but it doesn't affect. And adding an inert gas, like we said, group 18, anything in group 18 it doesn't affect. So yeah. So what is equal when the reaction reaches equilibrium? The rate of the forward reaction becomes equal to the rate of the backward. This is just the meaning of equilibrium. Like, you have to know here. So they're saying what will happen upon the cooling on the Gulf system as it has reached equilibrium. And they said that this reaction is endothermic. So there's gonna be, the temperature is gonna be here. Okay. Since it's endo, okay. So they said what will happen upon cooling. So you're removing heat. And when you're removing heat, what will the system do? They will try to increase the heat. So the system will try to increase. So if the system will try to increase, how will you increase? By moving to the left. So we need to read the statements and see which one like is correct about moving to the left. Okay. So the reaction produces more heat to reestablish equilibrium. Yeah, it's going to produce more heat because we said we're increasing, because the system is trying to decrease the heat. They're trying to decrease the heat in the system. We counteract it by increasing the heat, which will produce more heat to reestablish the equilibrium. So this is correct. The forward reaction is favored. We said that it will move backward because we want to increase the heat for the system. And yeah, so the forward reaction is not favored, it's the backward reaction. So that's why this is wrong. The system shifts to the left. Yeah, like we said, it moves to the left because, yeah, we said already. The mass of B stays the same as it is a solid. B does stay the same, like not stays the same, like B is not affected because it is a solid, but if we change anything, it changes with it, it just doesn't get affected. So that's why this is wrong. The concentration of D decreases. Since we're going to the left, D is giving more there, so it's decreasing. So that's why this is correct. Basically, it says which of the following is affected by the addition of a catalyst. So we know that a catalyst doesn't affect like anything like pressure, concentration, volume, anything like that. It doesn't affect it. It just makes the rate of reaction faster to reach equilibrium faster, but it doesn't affect the actual reaction. So the concentration of hydrogen gas, no, it does not affect. The activation energy, you just have to memorize this. The rate of the forward reaction and the rate of the backward reaction, these two are correct because it will make it go faster. Like we said, catalyst increases the rate of backward and forward reaction, but it does not affect the reaction. That's why that is correct. And the pressure of the system, like we said, is wrong because it does not affect. The rate of the forward reaction is equal to the rate of the backward reaction at equilibrium. I think we've gotten this by now. It's just memorizing. Okay, so here they're saying if they remove H2O, so if they're trying to remove H2O, the system will try and increase the amount of H2. Sorry, not H2O, H2. So if they want to increase the amount of H2, you're obviously going to move backwards. So that's why backward reaction is favored, and the amount of ammonia, which is NH3, will decrease because it's giving it here, which will make reactants increase and products decrease. That's why this decreases. Here, this is kind of a memorizing question. So a dynamic equilibrium is reached when the forward and backward reaction occur at the same rate. So we know equilibrium, they happen at the same rate, and dynamic means like it keeps moving, so it keeps moving at the same rate. The macroscopic properties of a system at equilibrium are constant. I think we did a question similar to this. Macroscopic means something you can see, like color, temperature, concentration, or pressure. So they're saying it's either macro or micro from the options. It's gonna be macro because macro is something you can see, and at equilibrium it has to be constant. So let's say, like I said, color, if you add a solution, you add color to it and it keeps like switching color, like let's say dye, you add it, it's gonna be like a drop of color, and then in the end it will be one whole color, like let's say blue. It will not continue to change to purple or something. It won't. That's why it's constant. But micro will keep moving, but you can't see it. Will keep moving, but at the same rate. So yeah, this question is memorizing. This question is kind of weird, but anyway. So basically they're saying a yellow solution, which is this area, the reactants, react to the colorless solution of KSCN to form a deep red complex, FeSCN, whatever. So they're saying the color of the solution becomes darker upon adding KSCN. So here it's deep red because of SCN. If you add more KSCN, you're adding more of SCN. So adding more of that will make it a deeper red, so it does go darker. Okay, that's why this is gonna be the answer, because adding, since this is yellow, okay, adding this will make it deep red. Adding more of this will make this darker and more red. So that's why this is the answer. The color of the solution becomes lighter upon adding this. So you basically have to memorize that adding Na2HPO4 takes away from Fe3. You have to memorize this. So since it takes away from Fe3, if you're decreasing Fe3, you want to increase, the system will try to increase it. And how will it try to increase it? By moving backwards, and by moving backward it will make Fe3 get more, which makes the solution lighter, which is adding more yellow. So I hope you understood from explaining that. And the reaction is reversible. If you see these arrows, this is reversible. If you see this is irreversible. So this is kind of the same as question 14. So upon adding FeNO3, the color of the solution, we have to figure out what happens. So adding Fe and adding SCN will make a deep red, which is this. If you add more of FeNO3, you focus on the Fe. You're adding more Fe, which will make this darker, like this area. So if you add more Fe, obviously the solution will become darker. Okay. Ag ions react with SCN ions to form a solid, AgSCN. So if you add AgNO3, like we said in the last question, that thing that had nothing to do with the equation, it takes away from Fe. Here, adding AgNO3, do you see AgNO3 anywhere in the solution? No, that's why it will also take away from Fe, making the solution faint. So that's why this is the answer. I don't like these questions because they're very weird. Here, the first equation, you have to memorize it. It's the same as this one, 14 and 15. You have to memorize this. Whenever they say KSCN or Fe3, anything like that, it's going to be Fe3 plus SCN and FeSCN. You have to memorize the charges and the thingies. So Fe3 plus, just memorize that, aqueous, they're all aqueous. Okay, SCN minus, and then FeSCN 2 plus. Okay, just memorize this. And now we'll do the second part. Calculate the number of moles of Fe3 plus ions and SCN ions. So you're gonna look here. They gave you volume and concentration, and they gave you here as well volume and concentration. So you're gonna do N equals volume times concentration. So remember the rule NCV. Yeah, so that's the rule. C is 0.020. We're doing Fe3 plus, which is first, which is this. Okay, 0.02 times, volume always has to be in liters, so milliliters to liters is divide 1,000. Okay, so when you divide 15 ml by 1,000, it's going to be 0.015. When you put this on the calculator, you get 3 times 10 to the power negative 4. You have to put it in scientific notation, so 3.0 times 10 to the power negative 4. So that's for the first one. And then the second one, they asked for SCN. So this is KSCN. You're going to look here. N equals C times V. Okay. 250 divided 1,000, it's gonna be 0.25 times 2.76. It's gonna be equal to 0.69 moles. Yeah, those are the answers. Okay, and then here, which of the following is true about the system? The reaction almost goes to completion. Basically, Fe3 plus is so much less than SCN, like you can tell. So since this is so small, since this is so small, it gets used up in the reaction, like almost gets fully used up in the reaction, and this will like stay the same because you're reacting most of this. So the reaction almost goes to completion. Yeah, and the amount of KSCN is so much larger than that of FeNO33. Yeah, that's correct, because look at the difference. This is 0.69. This is like you move it backwards like 1, 2, 3, 4. So it's gonna be like this, 0.0003. So that's why it's so much smaller. And the reaction does not occur, it does occur. The amount of, and we just said that this is the answer, not this. So yeah. You have to memorize that Le Chatelier's principle is, because they might ask you what is Le Chatelier's principle. They're not gonna ask you what is the meaning of this. You never know. So the principle states that the equilibrium state is subjected to a change. You have to know that it tends to counteract partially. Okay, counteract as in, like, let's say this is they said the reaction decreases. What will the system do? The system will try to increase it. So counteracting it, and partially, not completely. We're gonna analyze the graph. Okay, it looks very confusing, but like once you know it, it's so easy. Like, don't let the question like scare you. So we have the options: adding I2, removing Cl2, or increasing the temperature. So you're gonna look at the graph. You're gonna see that I2 just jumped randomly and increased, and ICI just like stayed normal. So from the option, what suits this graph most? Adding I2, because it increased, so this is correct. Here I2 barely changed, like barely, and Cl2 decreased. So which one of the options seems most accurate? It's removing Cl2. So since, because it decreased. Okay, here I2 barely changed, ICI lowered a bit. So increasing the temperature, if you increase the temperature, the system will try and decrease the temperature. And since the system is trying to decrease the temperature, and the temperature is here, so it's exo, if you're trying to decrease the temperature, you're going backwards, and ICI will decrease and I2 will increase by a bit. So that's why this is correct. And since you know these two, you could just like pick the last option for that one if you don't really know. For this question, it's really easy. So we're gonna look at the graphs and we're gonna look at what they gave us. So at time I, so we're gonna look at I, which is over here. Before we start, if you see something like this, that means something was added because it randomly increased. And when you see something like this, that means it just increased. Or if you see it like downwards, it decreased. So here there's this, so that means something was added. You look here, Cl2 was added, so that's why this is correct. So at time II now, we're gonna look at II, which is over here. Okay, so as you can see, COCl2 decreased. See, it went down, and Cl2 increased, and CO increased. Since this is negative, it's exo, so plus 107.6. So we're gonna look here, and since COCl2 decreased, how will we know if the temperature increased or the temperature decreased? So let's try temperature increased, and then we're gonna try temperature decreased. Okay, if temperature increased, the system will try to decrease it. So if they want to decrease the temperature, they're gonna move backward. So COCl2 will increase and COCl2 will decrease. So this is basically what the graph is. But let's say we did temperature decrease, the system would try to increase the temperature. And if they try to increase the temperature, that means they will move it like this, so forward, and COCl2 will decrease and COCl2 will increase. And that is not the graph, that is the graph here. See, it increased, and then here decreased and decreased, which is what is accurate. So temperature increase is going to be for II, temperature decreased is going to be for IV. And then so we did this. Now at time II, you're gonna look here, you see this. Remember I said when you see this, that means something was added, and so COCl2 was added. That's it. When the temperature of this reaction is increased, so if the temperature of this reaction is increased, the system will try and decrease it. So the equilibrium constant will decrease. Okay, when the volume of the container is increased, so you know when the volume is increased, the system will decrease the pressure. And when we said that when the pressure decreases, it will move to the side with more moles. So here there's 5 moles, and here there's 4. So which side will it move to? It will move to the left side, and the amount of Cl2 will decrease because you're moving there. And when a catalyst is added to the system, the equilibrium concentration of Cl2 will stay the same because a catalyst does not affect equilibrium, it just helps reach equilibrium faster. This question, we did a lot of these, so this should just be easy by now. If NOCl is decreased, the system will try to increase NOCl. So how do you increase it? By moving forward. So NO decreases and Cl2 also decreases. Okay, part B. If they say the partial pressure of O2 is increased, so the system will try to decrease the amount of O2. By decreasing the amount of O2, it will move forward, so N2 will decrease and NO will increase. So they said the gas mixture is compressed, so we need to count the amount of moles. So on the reactant side we have 4, and on the product side we have 3. So it's gonna move to the side with more moles, less moles, so the amount of N2 will increase and the amount of NO will decrease. Part B is really easy, I think we know it by now. Which of the following can alter the equilibrium state of a system? Changing the temperature, changing the concentration of a species, adding catalyst does not affect the equilibrium, and adding an inert gas also does not affect equilibrium, which is group 18. This is memorizing, and I'm sure you know it by now. Okay, another easy question. How will the equilibrium concentration change if the pressure in the system is increased by adding an inert gas? remember, inert gas does not affect equilibrium, so remains constant. How will the equilibrium concentration change if CO is increased? So you're trying to decrease CO. The system will try and decrease CO. If you want to decrease CO, you have to move forward. So CO2 will increase and NO will increase, and these will decrease. With another super easy question, what will happen if you remove water? Water is a liquid. Nothing happens if you remove or increase anything liquid or solid. So remains constant here. If the mass of AgCl is increased, remember AgCl is solid, so like I said, solid and liquid remains constant, does not affect equilibrium. If it was gas, that would be a different case. So here they said the pressure is doubled. That means pressure increased, and if pressure increased, we said it moves to the part with fewer moles. Okay, so here there's 3, here there's 2. It will move forward, so H2O will increase and H2 will decrease. And here, if argon gas is added, argon is group 18, so it's inert gas, so it's remain constant, because it doesn't affect equilibrium. Here they said if the pressure is half, that means pressure is decreasing. If the pressure is decreasing, it's going to move to the side with more moles. So here there's 1.5. I honestly don't know. Here there's 1. So it's gonna move like that. So backward, O2 will increase and SO3 will decrease because it's moving backward. And how would the equilibrium concentration change if the temperature is increased? If temperature is increased, the system will try and decrease the temperature. If this decreases, you want to move backwards, so moving backward will make O2 increase and SO3 decrease. Here again, if the volume is increased, the system will try and decrease the pressure, and if pressure is decreased, it will move to the side with more moles. So where's the side with more moles? Here there's 1. Here there's 2. It will move forward, so NO2 will increase and N2O4 will decrease. Here, how will the equilibrium concentration change if temperature is decreased? If temperature is decreased, the system will try to increase the temperature, and if they try to increase the temperature, it will move backwards, so NO2 will decrease and N2O4 will increase. At this point, you have to have like mastered backward and forward reactions. Okay, so if the number of moles of NH3 is decreased, that means the system will try and decrease the number of NH3. So if they try to decrease the number of NH3, you're gonna move backwards, so H2 and N2 will increase. How will the equilibrium concentration change if a catalyst is added? A catalyst, again, it will remain constant because it does not affect equilibrium. It just makes the rate of reaction faster, like to reach equilibrium. That's it. Okay, here, adding H2. So if you add H2, you want to decrease, the system will try and decrease H2. So by decreasing H2, you're gonna move backwards. So you shift to the left, H2O will increase and O2 will decrease. Now adding HE. HE is a noble inert gas, so it's group 18, so it will remain unchanged. Increasing the temperature, so the system will try and decrease the temperature. So since it's endothermic, because it's positive, plus 242, and the system tries and decreasing it, it's gonna move forward, so shifts to the right, H2O will decrease and O2 will increase. Now the second part, which of the following would decrease the concentration of CO? So we have to see what will like make CO decrease. So adding H2, if you add H2, the system will try and decrease the amount of H2. So if you try and decrease the amount of H2, you will move backward, so CO will decrease. So this is correct. Decreasing the temperature, if you decrease the temperature, it's endothermic, so plus 131. If you decrease the temperature, the system will try and increase the temperature by moving backwards. So also backwards, it's going to decrease the amount of CO. Adding C, let's see. Adding C, if you add C, the system will try and decrease the amount of C. So if you want to decrease the amount of C, you're going to move forward, so it's going to increase the amount of CO, so it does not decrease the concentration of CO. This is wrong. Adding a catalyst does not affect equilibrium. Increasing the temperature, since we said decreasing the temperature is the answer, increasing is obviously not going to be the answer. Here the rule for K is products over reactants. Okay, and we're not gonna take anything solid or liquid, we're only gonna take gas. Okay, so here solid, ignore. Here liquid, ignore. We'd only take this, so it's gonna be K equal Cl2. Okay, here liquid, ignore. Gas and gas, they're gonna be. Also, if it's like this, you're gonna put it up like K equal H2, like it can't have like a number in front of it. You're gonna take that number and you're gonna put it here, so it's gonna be 2, and then O2. And then the last part, they're both gases, so you take them both. You're gonna take the products first, so K equal NO2, and then take the number in front and put it on top, and then over N2O4. That's it.